Thanks again. So on behalf of our team, DeepOutbreak, it's me, Aditya, and I'm, as was Satya, and Alex Rodriguez, who's actually a PhD student who's doing research in our group at Georgia Tech. So first of all, a quick shout out to all the awesome members in our team. Apart from us, it's Dr. Vijay Adhikari from the University of Iowa, Dr. Naren Ramakrishnan from Virginia Tech, and a great slate of PhD students. Who, as you can imagine, did most of the work. So Nikhil Muralidharan from VT and Anika, who's also a PhD student in our group. First of all, thanks a lot to the organizers and the sponsors for organizing all this challenge. It was really exciting, and also a big thanks to the judges whose helpful feedback really helped improve our work throughout the course of this contest from semifinal to the final. So a bit of a context, right? We have been, so all of our team members are coming from a data science, machine learning, artificial intelligence background. And one of our lab's focuses has been on exploring the performance and utility of data-driven methods in public health. So broadly, like we have been involved in many other projects ranging from surveillance, interventions, vaccination campaigns, distributions, and so on, right? And in all of these things, one of the visions which is really tying everything together is to really see and explore how useful data can be, purely data-driven methods can be in providing a complementary perspective to traditional models. And so the context has been in developing data-driven methods for all of these kinds of different public health problems. And we believe that data from multiple sources is often very sensitive and more sensitive to what is happening on the ground, so to say. So one good example of this line of work from our group has been on AI models for forecasting. We have been doing this for a few years. So apart from writing research papers at AI and machine learning conferences, we also try to participate very actively in CDC forecasting initiatives. So for example, we have been participating in the influenza-like illness count prediction projects at the CDC for multiple years. And of course, when COVID struck earlier this year, we all were trying to see how we can help. And we also participated then and subsequently in COVID mortality predictions, where we are trying to do weekly reports, and also daily COVID-induced hospitalizations. So in fact, we were one of the first couple of teams to do that on the CDC website as well. And then we contribute to this COVID Hub Ensemble. So this is a bit of a context of where we are coming from, right? And so given that we were doing this, then we got to know about the challenge goals, and two things out of the challenge really struck us, which was one of which was using survey data. So we love data, right? I mean, we're coming from that perspective, and we using survey data to enable situational awareness, and also if the integration of this data leads to greater sensitivity, specificity, and timeliness. So all of these keywords really appealed to us, and it felt like the work we were doing was a natural fit, so to say, to this challenge. Hence, our entry really focused on, our submission to the challenge focused on trying to predict COVID and flu. So the motivation so this was summer of 20, right? And the motivation really came from, as a lot of folks were worried that any second wave of COVID was likely to coincide with the flu season, and hence forecasting flu burden as well was becoming crucial. So as it's well known, accurate forecasting gives valuable lead time. And that eventually trickles down to better interventions, so more data for interventions, deciding for policymakers, and also optimizing supply chain decisions. So hence our aim, and the aim of our submission was to jointly forecast flu and COVID. And we wanted to really explore the utility of syndromic data like the symptom survey data for short-term forecasting of these diseases. So what are the main issues here? One of the main challenges which we faced where we're trying to design this data-driven approach was that these diseases are very symptomatically similar, right? So hence the surveillance systems are susceptible to these similarities. And just like a quick picture, right? And you don't have to understand all the curves, but the main point is if you look at the right-hand side of this yellow highlighted part, you can see that the current season, which is given in black, bold black, is very different from all the historical seasons which you're seeing. This is the influenza, number of influenza outpatients data coming from the iLinet surveillance systems of the CDC. So it's very clear that, and this is the point when the national emergency was declared on COVID. So you can see that how it's very non-trivial how they interact and how they can, in some sense, contaminate each other, right? These surveillance systems. And the additional main challenge was also that COVID being a really emerging novel scenario, you don't really have that much data. Even the systems for collecting the data were not well developed at that point. And it's really and you really need robust AI and machine learning techniques to extract the maximum knowledge out of these of this kind of a situation. Hence, our approach was pretty, I think, again, natural in hindsight, which was leverage the historical flu data, because we have a lot of that, thanks to the hard work from CDC for the past 20 years, and then also leverage these new signals which people are volunteering to collect, which are related to COVID. So this can be like line list data from the CDC, like Johns Hopkins, mobility data, testing data, and a whole slew of them. So we are using many different signals. But the main thing which we want to highlight is that, remember, one of the main challenges was the symptomatic similarity of these diseases. And that's where the FP symptom survey data was really especially useful, because they were like COVID CLI, which is COVID-like illness, and WILI, which is influenza-like illness surveys as well in that data. So again, this feel like a natural fit to us in the sense of what we really wanted to do scientifically, and also what was available, being made available to us from the challenge. Okay, so long story short, we designed new deep learning based models. I won't go into the details, but there are a lot of cool AI problems here about steering historical deep learning models using transfer learning and knowledge distillation, and also how do you develop robust models which are also give you principal uncertainty estimation. So these are all classic, in some sense, AI problems, and this gave us a nice playground to test out our ideas and methods. And it seems like our method seemed to work well. For example, just a quick rundown of performance, just raw accuracy, right? So if you look at forecasting the influenza curve, which is the ILI in presence of COVID, our method, which is in the red, is like adapts better to the scenario than almost like in 10 out of 11 regions from all the other state-of-the-art methods, including like the national region. And in addition, for COVID mortality and hospitalizations, which our group, as I said, has been participating at the COVID hub, our point predictions on an average have been more accurate than the official ensemble. And also the probabilistic predictions are very competitive. So it seems like, okay, we developed a deep learning couple of deep learning models, and then it seemed to perform well in raw accuracy. But now I'll take it to Alex, who can talk a little bit more about a few experiments on how do we explore symptom data utility itself. Alex.
Thank you, Aditya. To explore different facets of the utility of survey signals in forecasting and in the pandemic, we asked specific questions. First, do survey signals help with overall performance? Second, what is the predictive power of the symptom signals? And third, which aspects of forecasting do survey signals contribute to? Please, next. For question 1, we compare our CDC submissions for COVID forecasting with the same model, now including the survey signals. This is a US heat map depicting the percentage of change in forecasting accuracy. The more green indicates that adding survey signals help more in forecasting accuracy, and more brown indicates that they are not helping. We found that survey signals help in 21 of the 51 regions evaluated. On the other hand, for the regions in brown, based on our experience with our model, we suspect these regions may require more statistical support in the data collection. Next, please. Here we want to understand the predictive power of these symptom signals alone. In the plots, the golden line are the predictions for our model only using survey signals. We found that for short-term forecasting, performance very comparable to the model with using all the signals. However, for longer term, they usually overpredict themselves by themselves, but it still corroborates the correct trend. Therefore, in general, we recommend to use them in conjunction with other signals. We have more examples in our white paper. Please, next. Which aspects of forecasting does survey signals help in? We have already saw that it helps in raw performance, and also we found that it helps in anticipating trends. We present here ILI and COVID examples, but let us focus on the COVID examples in the right. Look at the blue dotted line. Without survey signals, the predictions are going down, while ground truth is going up, which is the red one, is going up. In contrast, adding survey signals, which is the rightmost plot, help us to anticipate the upcoming trend. We have more elaborated discussion on this point in our white paper. Now I pass back to Aditya. Thank you.
Great. Thanks a lot, Alex. So a quick summary of what we found, just what Alex described well, which was, do survey signals help with performance? The answer is clearly yes. And they are in fact mostly complementary to the other data sets we used, and it also helps improve performance in a majority of the regions. What is the predictive power? We found that it was especially powerful for short-term forecasting, like 1 or 2 weeks ahead, right? Or 3 weeks, up to 3 weeks ahead. And sometimes the survey signals alone give a very unique perspective. Like, for example, as Alex showed, it can also lead to changing trends, and which is very valuable, especially as we are interested in lead times. And for longer term forecasting, we found that we should use it in conjunction with other signals for that. And what aspects does forecasting contributes to? So we generally found that it helps in anticipating future trends in addition to clear accuracy. So what's next, just to conclude? So the research which this triggered, we wrote a couple of research papers, and they'll be appearing at the top AI conference in early next year. So there are many open technical questions here, which makes us also happy. At the same time, we are continuing to submit to CDC, incorporating survey signals. So that is important work which we do every week. And more complementary dimensions which we are exploring is to incorporate other sorts of data sets as well, right? So for example, point of care information and more behavioral data. And this is where I feel that the survey signals and the symptom data which was released was so valuable. I mean, like, for example, vaccine adaptation, distribution. I think this would be really crucial in the coming months to do a better job at these forecasting tasks. And we are also exploring many other things in context of extending these techniques to hospitals, where we are doing this in context of hospital-acquired infections like C. diff and COVID as well there. And campus situations like which can guide reopening policies, and also extend it to other geographical regions. So we have a bunch of projects. So we are looking forward for partners. So if you're interested, just shoot me an email. So thanks again to everyone, and also the data collection volunteers. I think without them, we would not be able to do all of this. And yes, thanks. Any questions?
Question from me. This is Christina. Good to meet you. So how has your work, your research changed since the start of the challenge? Has anything sort of improved along the way? Can you share any lessons learned?
Definitely, Chrissy, that's a good question. So I think one of the things we were hoping for, and I think that's what I was trying to emphasize here, so maybe I'll quickly share that slide, was that so really trying to forecast both flu and COVID, we needed some symptom data to do that, because they share symptomatic similarities. So some sort of symptom survey data can help us tease out that difference and do a better job at that prediction. So that's where I guess it was a very good fit with what this challenge was itself giving out, and that's why we thought that this would be great, and that has led to clear improvements in performance. As I said, we are doing very well in both influenza as well as the COVID forecasting. So clearly the data release has helped us really tune our method to that.